Good morning, children. So today I am discussing the next topic, that is Lorentz force. So what is the concept behind it? That if you take a charged particle, suppose you have taken a charged particle Q, alright, it is moving in a magnetic field. So magnetic field, we denote it, magnetic field strength, we denote it by capital B. So suppose the charged particle is moving in a magnetic field with a velocity v, making an angle theta with the direction of the magnetic field. Then, due to the motion of the charged particle in the magnetic field, it will experience a force which, according to Lorentz, given by QVB sine theta. Alright? Means how much force the charged particle will experience? QVB sine theta. So this is known as Lorentz force. So what is the basic concept? That when a charged particle moves in a magnetic field, alright, it experiences a force which is given by, according to Lorentz, Q, the charge, amount of charge present in the particle, multiplied by V, speed of the particle, then B, the magnetic field strength, and sine theta. What is theta? Theta is the angle between the direction of motion of the charged particle and the magnetic field. So here, a nice thing you will observe that, you see, when theta is 0, then force will be 0. Alright, what does it mean? That when the charged particle is moving along the direction of the magnetic field, alright, charged particle is moving along the direction of the magnetic field, then what will be the force? It will be QVB sine 0, that is 0. So it is a very nice thing in science, in physics, that when a charged particle moves in a magnetic field, it experiences a force, but if it moves along the direction of the magnetic field, then it will not experience a force, or according to Lorentz formula, according to the concept of Lorentz force, the force acting on the charged particle will be 0. Alright, now if you apply this concept on a force acting on a current carrying conductor, understand it? When a current carrying conductor you are placing in a magnetic field. Now, current carrying conductor, how the current moves through a conductor? When the electron moves within the conductor, alright, or according to our concept of current, we know positive charges, amount of positive charge flowing per unit time is known as the current. So what does it mean? The moment you are saying current carrying conductor, it means that within the conductor charges are moving. Alright, and you have placed the conductor in a magnetic field. So what will happen? The moving charges inside the conductor will experience a force. So we can say that as a whole, conductor will experience a force when it is placed in a magnetic field. Alright, now the question arises, how much force it will experience? Now, if you place, as I already mentioned, that a current carrying conductor in a magnetic field, then it will experience a force according to the concept of Lorentz force. That experimentally also you can find out. Okay, what is the experiment for that? You see here a stand and clamp is taken, and then by means of thread, this is thread. By means of thread, what is suspended? A conductor is suspended. Suppose I am naming the conductor as AC. Alright. Because B for magnetic field, that's why I have not used. So a conductor is suspended and the conductor is connected to a battery, key and rheostat in series. Alright. And where the conductor is placed, that is the most important concept, understand it. It is placed in a magnetic field. Here you see I have not drawn the magnet. It is north and it is south. Alright. Means what? I am just showing you how it is placed. If this is the conductor, then the horseshoe magnet, a horseshoe magnet is kept like this. My thumb is North Pole and the index finger is the South Pole. So the horseshoe magnet is kept like this. You have understood? So as it is a three-dimensional diagram, that's why I have not drawn it. So don't get confused. These N and S are what? N and S are the two poles of a horseshoe magnet. And once again I am showing you how the horseshoe magnet is placed. If you consider this is the straight conductor, then horseshoe magnet is placed like this. Alright, you see this is horseshoe magnet, this is the horseshoe magnet, and how it is placed? So that north is in downward direction and south is in the upward direction. What does it mean? Just understand it. Magnetic field is acting in the, magnetic field always act from north to south. So magnetic field is acting in the upward direction. And if you consider the connection of the battery, the moment the key will be closed, current will flow in this direction. So in which direction the current is flowing? In this direction. Now look at the diagram. Current and the magnetic field, they are perpendicular to each other. Now, what is the observation? This is the experimental setup. The moment you will close the key, you will see the conductor, it will move towards you. Means, suppose here magnetic field is in this direction, current is in this direction, and this is the conductor. Conductor will move towards you. Conductor will move in the outward direction. Means what? It is experience a force in the outward direction, and that's why it is moving towards you. It is moving towards the observer. Alright? Clear to everyone? Now, it has been found experimentally that the force experienced by the conductor, it is directly proportional to the current. Alright, if you increase the current, it will experience more force, it will move towards you by more amount, and if you decrease the current, then the force experienced will be less. And it has been observed that it is proportional to length of the conductor. Okay, what is I? I is the current passing through the conductor, L is the length of the conductor. Then it has been found that force is directly proportional to the strength of the magnetic field. If you increase the strength of the magnetic field, then it increases. Another point you will observe that F also depends on the angle between I and B. In this particular case, the angle is 90 degree. But it is not mandatory that always you have to place I and B 90 degree. Okay, you may place it in any direction. Alright. But so you will see that it is proportional to sine theta. Means the sine of the angle between I and B. What does theta represent? Theta is the angle between the direction of current and direction of magnetic field. I repeat, what does theta represent? Theta is the angle between the direction of current and direction of magnetic field. So if you combine all this together, then you can write F is proportional to ILB sine theta. Is that clear? F is equal to ILB sine theta. Constant of proportionality is taken as 1. Is that clear? Now, you see, this relation is very, very important because it gives you the amount of force experienced by a current carrying conductor placed in a magnetic field. Alright, so the question arises that why a current carrying conductor experiences a force when placed in a magnetic field? Two ways you can explain it. The first way I have already explained, that current means the charges are moving within the conductor. So when a charge moves in a magnetic field, then it experiences the Lorentz force given by QVB sine theta. So that is the force experienced by one charge, isn't it? Q amount of charge. So if you consider the current I is equal to Q by T. So what is happening? That due to the current, all the moving charges, they are experiencing a force. The total force experienced by all the moving charges is the net force acting on the current carrying conductor when placed in a magnetic field. Okay, this is one way one can explain. Another way we can explain the same thing. You see here, When current passes through a conductor, then we know that surrounding a conductor, a magnetic field is produced. We know no magnetic effect of current. So that explanation is not given in the book, but you should know it. That's why I am discussing that when current is passing through a conductor, then it produces a magnetic field surrounding the conductor. So you see, when you are placing a current carrying conductor in a magnetic field, how many magnetic fields are there? Two magnetic fields. Alright, one magnetic field produced by the horseshoe magnet or any other magnet you have used. Another magnetic field is produced due to the current passing through the conductor. So these two magnetic fields interact, and that's why it experiences the force. Here one point you should remember, that when the force is experienced, the magnet will also experience the force, conductor will also experience the force. Now in this case, conductor is movable, so conductor under the action of the force, it is getting displaced, it is moving. Alright, but if you do this, that you are making the conductor fixed and you are taking the magnet which is movable, then what will happen? The magnet will experience the force, and under the action of the force, magnet will be displaced. Alright, so this is the basic concept. So what you have to remember for your board exam point wise, that is, when a current carrying conductor placed in a magnetic field, it experiences a force given by, okay, forget whatever I said so far, forget the Lorentz force, but you have to remember this, that whenever a current carrying conductor placed in a magnetic field, how much force it will experience? ILB sine theta. I is the current passing through the conductor, L is the length of the conductor, B is the magnetic field strength, and theta is the angle between I and B. Alright, now you see the special case. When theta is 90 degree. Alright, theta 90 degree means what? I and B, they are perpendicular. When I and B, they are perpendicular. You see that direction of current, direction of magnetic field, they are perpendicular to each other. Then what will be the force? Force will be ILB. Is that clear? Now, from this one, this relation is very important, because from this one can define what is the unit of magnetic field strength. Now, what is the SI unit of B? I am writing B, but I am saying verbally this is magnetic field strength. So, you too should remember it. What does B represent? B is the magnetic field strength. Now, SI unit of magnetic field strength is Tesla. Alright, SI unit of magnetic field strength is Tesla. It is after the name of a physicist. Alright, so that's why when you are writing the full form, it should be TESLA. But when you will write down only the first word, then it will be capital T. All of you have learnt it in 9th standard. Okay, how to write the unit. So as Tesla is the name of a scientist, so how to write? If you are writing the full form, T should be small, but if you are writing only the abbreviation, then T should be capital. So what does Tesla represent? Tesla is the SI unit of magnetic field strength. So you see, from this formula, F is equal to IBL. You can write B is equal to F by IL. Alright. And this relation is very important from the point of view of board exam also, concept wise also, that by utilizing this, one can define 1 Tesla. Alright, now as you know, I always prefer that no definition you should mug up, so understand it, how the definition of 1 Tesla is coming. Now you see, if you consider F as 1 Newton, I as 1 amp, L as 1 meter, then what will be the value? 1 by 1 into 1, that is 1, then B will be equal to 1 Tesla. And here you have to remember that theta is 90 degree, that's why sin 90 is 1. Otherwise, what is the formula actually? F is equal to IBL sin theta. Is that clear? Now theta is 90 degrees, so better I am writing here IBL sin 90 degree. because sine 90 degree is 1. So you can write like this. So understand it. When I is 1 amp, L is 1 meter and F is 1 Newton, then and theta is 90 degree, then B is 1 Tesla. So how you can define 1 Tesla? Alright, you see, you can define 1 Tesla this way. If a conductor, okay, of length 1 meter carrying a current of 1 amp placed in a magnetic field perpendicular to it experiences a force of 1 Newton, then magnetic field strength is 1 Tesla. So no need to mug up. Whatever written mathematically, just write it in statement. So I am telling it slowly, please note it down. If a conductor carrying 1 amp current having a length of 1 meter placed in a magnetic field theta 90 degree, how to say, placed in a magnetic field perpendicular to it experiences a force of 1 Newton. I repeat, if a conductor of length 1 meter carrying a current of 1 amp placed in a magnetic field perpendicularly experiences a force of 1 Newton, then magnetic field strength is 1 Tesla. So why this relation is important? Because from this relation you can define Tesla and it comes in board exam. So please learn the definition of 1 Tesla, as I said, utilizing this fact. Alright. Then the next thing is that I said that when the magnetic field is in the upward direction, current is moving towards the right side and then the force experienced by the conductor is towards you. How I have said it. So there is a rule for it. That is known as Fleming's left hand rule. Okay. What is the name? That is known as Fleming's left hand rule. Alright, now the diagram I will not draw. You too don't have to draw the diagram, but you should know how to apply it and what is the rule. What is Fleming's left hand rule? You see, you take the first 3 finger of your left hand. Okay, first 3 finger. What are they? Thumb, the index finger and the middle finger. Okay, how you place it? You place it, you just see all are perpendicular to each other. Is that clear? All are perpendicular to each other. Clear to everyone? Then, then middle finger acts in the direction of the current. Middle finger gives you the direction of the current. Index finger gives you the direction of the magnetic field, alright, and the thumb gives you the direction of the force, or you can say that the direction along which the conductor is moving. Okay, so what I am repeating it, what is Fleming's left hand rule? If you set the first 3 fingers, that is the thumb, index finger, middle finger, like this, perpendicular to each other, then if the middle finger gives the direction of the current, then index finger gives you the direction of the magnetic field and the thumb gives you the direction of the what? Force experienced by the conductor. Is that clear? So here there is a easy way to remember this. Alright. How you can remember this? You see, father, this is father, the thumb, mother, index finger, child. Father, mother, child. Is that clear? Father, F, force, direction of the force. Alright. M, mother, direction of the magnetic field. Then C, child, direction of the electric current. And you know, all child are like this, no? Always are ready to give the strong electrical shock to the parents. So you see here, this is child, electric current, always ready to give the electrical shock to their parents. And M, mother, magnetic field, by the attraction holding the family together. Then F, force, Always father controlling by applying the force, controlling the family. Alright, this is the joke I am making, just understand it. This is just a funny way to remember Fleming's left hand rule. How? That father, mother, child. Alright, start from father, mother, child. F, force, direction of force. Then M, mother, means magnetic field, direction of the magnetic field. Then C, child, direction of electric current. Alright, so by applying Fleming's left hand rule, one can find out, depending on the direction of current and direction of magnetic field, in which direction the conductor is experiencing the force, and if the conductor is free to move, in which direction the conductor will move. Alright, so you see that formula F is equal to ILB sin theta gives you the magnitude of the force, whereas Fleming's left hand rule, it gives you the direction of the force. Is that clear? So Fleming's left hand rule gives you what? The direction of the force experienced by a current carrying conductor when placed in a magnetic field. Alright, so these points, these two topics are very important. So kindly learn and practice it. Thank you, girls.